Welcome back. In part 13 of this lecture series, I'll shift from discrete point charges to continuous charge distribution. And one of the simple examples to which we referred in the last part, a circular ring uniformly charged with, let's say, charge cubes. This is a circular ring, but we are looking at it not from the front, from the side, and it looks like ellipse, but it's a circle, and let's say it has got total charge Q placed on it. We wish to find out the electric field at some point lying on its axis. Let's say at a distance x, I assume the radius of this circle to be a. So see, had there been discrete charges, what you can do, you can find out electric field due to individual charges and take their vector sum. But there are no individual charges placed like that in this case. So what would we do? We'll assume, we'll consider a small section of this circle. Let's say its length is dl and it has got charge dq. I'll find out electric field due to this small section at that point of observation P. Let's say due to this small portion the electric field is dE. Very easily you can reach out that dE can be resolved into two rectangular components, dE cos theta and dE sin theta. Now what happens if you take just diametrically opposite section of the section you considered earlier, that means somewhere over here, its electric field, make the same angle, its electric field would be like this, same in magnitude, but in a different direction. I can resolve it further. So what will happen? What I find that d sin theta component is in this direction and dE cos theta component is in this direction. You can very easily see that when I find out electric field due to whole of the circle, all the sign components due to diametrically opposite sections of the circle will get cancelled out, and the only component which will survive is the cos theta, and summing them up for a continuous distribution is what you call as an integration. If you want to learn more about integration and why we do integrate and what's its physical significance, you can refer to the lecture series on mathematical tools by me. Now the total electric field is dE cos theta integration over complete circle. Now just put in the value of dE. What was this a? This is x. This is under root a square plus x square. So what is electric field dE? It will be 1 by 4 pi epsilon naught small charge dq divided by under the root a square plus x square whole square. Square and under root get cancelled out, and cos theta. What is cos theta? Cos theta is base over hypotenuse. This is x divided by under the root a square plus x square. What you can do? You can find out dq first of all. If the circle has got circumference, what is the circumference of the circle? 2 pi a, and it contains total charge q. So what is the charge density? Charge density, let's say I call that lambda. Charge density would be total charge divided by total length. Total length of the circumference is 2 pi a. So if lambda will be q by, what would be the charge on small length dl? We assumed it to be dq. So dq would be lambda into dl, that is equal to q by 2 pi a into dl. Put in the value over here and integrate. 1 by 4 pi epsilon naught dq is nothing but q divided by 2 pi a into dl into we have got in denominator a square plus x square raised to power 3 by 2. Everything is constant. Take it out of the integration. The only thing remaining inside the integration is dl, and integration of dl over complete circle is nothing but its circumference. What does that mean? Integration also means summing up. Now this is dl, this is dl, this is dl, this is dl. When you will sum up all these dl's, what you would get? You would get 2 pi a. So the integration of dl is 2 pi a. The resultant electric field would be 1 by 4 pi epsilon naught q divided by 2 pi a square plus x square raised to the power 3 by 2 integration dl. And the next step, you can just put that equal to 2 pi a. This 2 pi a get cancelled and you get the final formula of electric field at a point on the axis of a uniformly charged circle as q by a square plus x square raised to power 3 by 2. And there is one, I think that I left out this x. This is x over here. This is the electric field. Now, can we do a special case for this? Just see if x is equal to 0. Now, this was the circle. And this was the point of observation. The distance between them was x. If you make x equal to 0, where will you reach? You will reach at the center of the circle. Just put x equal to 0. That means E at the center. If you put x equal to 0, E equal to 0. So we have reached out mathematically at a result which in the last part of this lecture series we reached out intuitively by seeing the generalization in the concept that when there is a regular distribution of charges around a symmetric regular geometric shape, the electric field at the geometric center would always be 0. We have reached out at this conclusion. You can physically understand this thing, that there are so many charges placed out, and at the center one is pushing in this direction, the other is pushing in the opposite direction. Similarly, all other sections, one pushes in this direction, the other pushes in this direction. The result is that you get 0 electric field. This is a good article, but there is very interesting corollary which we can obtain from this. What if x is quite large? Now earlier we made x equal to 0 and we reached out at the center of the circle. What if x is quite far away? That means x is very greater than a. If x is very greater than a, you can neglect a square in this relation. This x square raised to power 3 by 2, the 2 can cancelled out. You will get x cube in the denominator. E is equal to 1 by 4 pi epsilon naught qx divided by x cube. X get cancelled out, and what is the resultant formula? Q by x square. If you are careful, you can easily say that this is electric field due to a point charge. What does that mean? We were finding out electric field due to a circular charged ring, uniformly charged circular ring, and the result what we are getting is that that is same as electric field due to point charge. Obviously, if from a circle you go very far away, the circle will seem like a point, and the result followed is the same, the electric field due to a point charge. In other words, you may also say that when you are at a far off point, it will seem to you as if whole of the charge of the circle is not at its circumference, rather it is concentrated at the center of the circle. This is really interesting. The more interesting thing is that how mathematically you reach a point which is your which you can reach with the help of your common sense. A circle, when seen from a very far off point, will look like a point. And the mathematics also says the same thing. This is really interesting. Now, once we have started with this continuous distribution, there is an assignment for you again. And I hope that all of you are doing these assignments. Some are responding to me with the solutions on WhatsApp or other ways, but most of you are not doing the same. I request you to do all these assignments and revert back to me. Let's try to solve all these questions. Now these questions, starting from a little simple to a little difficult. You need not be able to solve all of them in the first go, but try them. What we found out in the last article was electric field due to a complete circle at a point on its axis. What about a semicircle? A charged semicircle having linear charge density lambda at a point at the center of the semicircle. At the center of the circle of which the semicircle is a part of. Electric field at this. Take radius to be, let's say, A. What would be your answer if there is a circle, but the one part of it has uniform charge density of positive charges and the other has got same charge density but of negative charge? Again, take the radius to be A. You need to find out electric field at the center. Can you do it for a quarter of a circle? And can we do it for a semicircle? But again, the upper half having positive charge, the lower half having negative charge. Can we do more? Can we do this? It may be a little tough one for you. Instead of a line, there is a surface charge. I got an inverted bulb, a hemisphere, having radius A, and there is uniformly charges distributed on all of its surface, the inverted surface. We need to find out electric field at the center. Again, take the radius to be A. And let's say charge density is sigma. Can you try this? I hope you can.